So let's get started. Okay, so we're starting a new chapter. The new chapter is focusing on more ways that you can do proofs. Now, ultimately, how do we prove something? What does it mean to prove something? Better way to say it, all your proofs are in the form of if-then statements, right? Any proof you've ever done could always be rephrased into if A, then B. If A is true, then B is true. If two integers are even, then their sum is even. Something like that, right? This is the same thing as A implies B, right? If A, then B is the same thing as A implies B. So when we show that an implication is true, we've proved something. There's logically equivalent ways of writing A implies B. There's more than one way of writing A implies B. You don't have to write A implies B directly. The same way that there's a lot of ways to write 10. I can write 10 like that. I can also write it this way. And maybe sometimes it's useful to think about 10 this way, and maybe sometimes it's useful to think about 10 this way, based off of the context of the problem that you're solving. So this is one way that we can think about an implication. This is the most straightforward way we can think about an implication. We're going to show you two logically equivalent ways of thinking about an implication, and then we'll do some proofs where you would think about it those different ways. Chances are a lot of you have heard about the first one. The first one is called the contrapositive. How many of you know what the contrapositive is? Just two of you? Okay. The contrapositive of A implies B is not B implies not A. Right? And these are logically equivalent. We'll prove it with the truth table, but first let's establish intuition. Let's see. I make the statement, if I'm wearing shoes, then I'm wearing socks, is logically equivalent to, if I'm not wearing socks, then I'm not wearing shoes. If I'm wearing shoes, then I'm wearing socks is logically equivalent to, if I'm not wearing socks, then I'm not wearing shoes. Another example. If there's smoke, then there's, no, what do we do? Oxygen and fire, that's one that helps. If there's fire, then there's oxygen, is logically equivalent to, if there's no oxygen, then there's no fire. You feel like your intuition's good and ready to do the proof? So let's fill out this big, ginormous proof table. So just got A, true, true, false, false, B, true, false, true, false. Okay, not A is going to be false.
False. True.
Make sure you still know how to do basic propositional logic. Not B is
False. True.
okay, A implies B. So true implies true is true. True implies false is false. False implies true is false implies false is okay. Now I told you that the contrapositive of A implies B is not B implies not A. So now let's check that. False implies false is
True.
true implies false is
False.
false implies true is
True.
true implies true is. So they're logically equivalent. So there's no difference between thinking about an implication this way or this way. They're logically equivalent. The same way that you can think about 10 as 5 plus 5, or you can just think about it as 10. They're logically equivalent ways of thinking about 10. These are logically equivalent ways of thinking about an implication. So let's do an example where we think about an implication this way instead of this way. So, quick proof. Let R be an equivalence relation on A, and let A and B be two elements in there. With me so far? Remember, what's an equivalence relation?
Means they're symmetric, transitive, and
Reflexive. That one's on the test, so make sure you know it. All right. So here's what we're going to prove. We're going to prove that if A is not related to B, then the intersection of the two equivalence classes is empty. Does everyone understand what we're trying to prove? Okay. The way that we're going to do this is like this. We're going to show that if this is not true, then this is not true. So I'm going to show that if the intersection is not empty, then A is related to B. Did everyone follow that, or should we write it out? Make sense? Okay, so let's do it. So, remember the way that you would do proofs like this. You'd assume the antecedent, and you'd show that implies the conclusion. Here we're doing it different. We're going to assume not the conclusion, and show that implies not the antecedent. You with me on that? So, assume not this. Assume their intersection is not the empty set. And then from here on out, just follows exactly the way you think. Okay, if their intersection is not the empty set, then that means there's something in there, right? So if their intersection is not empty, then there must exist something in there, call it x, in their intersection. Now if x is in the intersection of these sets, then x is in both sets, right? That's what we meant by intersection. Maybe it helps you if I put the logic in there. You good with line 2? Okay. But what does it mean for x to be in A's equivalence class?
Then X is related to A.
Then x is related to A. And since it's symmetric, that also means A is related to x. Similarly, if x is in B's equivalence class, that means x is related to B. So if x is related to A and x is related to B, and then I just write that means A is related to B. How? Because R is the equivalence relation, so it's transitive. So if I have A is related to x and x is related to B, then I have A is related to B. Make sense? Yep. Okay. So notice what we did. We assumed not the conclusion and showed that implied not the antecedent. We're done. So 2 ways to do proofs now. You can assume the antecedent, show it implies the conclusion. Or you can assume not the conclusion and show that implies not the antecedent. However you want to do it. Okay. Next proof style is a proof by contradiction or a reductio ad absurdum proof. Here's the thinking behind this proof. Remember, we're trying to show here that if A is true, then B is true. Right? The way that we're going to do this with proof by contradiction is we're going to say, assume A is true. We're going to say if A is true and B is false, and not B is true, or B is false, we're going to show that this leads to something impossible. In other words, it was impossible for A to be true and B to be false. Right? I don't know. I'm trying to come up with a way to help that make sense. Is that still weird?
A little bit.
Okay. So we're doing our proof, and we start out with A, right? We're trying to show that A implies B. Show A. If I show that and not B being true, and not B being true, leads to something that's impossible, then not B couldn't have been true. So not B had to be false, so B had to be true.
Okay.
That's the thinking there. Now, we'll do it in a... We're ultimately saying that showing this, showing that A and not B leads to something impossible, is logically equivalent to A implies B. But this is why it's called a reductio ad absurdum proof. This condition leads to something absurd, something that can't be true, something that's for sure false. Right? So let's do an example of that, and then maybe let's do the truth table, do an example, do 2 examples. I want to do 2 examples of this one because it's a little bit more weird. And then see if you have any more questions. Oh, I did 3 proofs by contradiction. All right, so let's go through, starting with this one. Oh, let's fill out the truth table real quick. All right. So true and false is
False.
false. False implies false is
True.
true. All right, next one. We have A and not B. We're ending these two together. True and true is
True.
true implies false is
False.
false. Right? False and false is
False.
false and false is false.
Mhm.
And then false implies false is.
True.
And then finally, false and true is
False.
false. False implies false is
True.
true. Okay. So this column's the same as this column. Yep, they're logically equivalent. Okay. So let's do some proofs by contradiction to help you get a feel for it. Okay. This one. If x is an integer, so x is an integer is going to be our a, then x is not both even and odd. X is not both even and odd is our b. Right? So instead of showing that a implies b, we're going to show that a and not b implies something that's false. So if x is an integer, then x is not both even and odd. So how are we going to do this? We're going to assume, by way of contradiction, that x is an integer, a, and x is both even and odd, not b. And we're going to show that this leads to something impossible. You with me so far?
Mhm.
Okay. So we assume that x is an integer that is both even and odd. Well, what does it mean for x to be even? That means it's divisible by 2, or in other words, there exists some integer a such that x is equal to 2a. Also, since x is odd, that means there exists some integer b such that x is equal to 2b plus 1. So you go with line 2?
Yep.
Okay. Is x equal to x?
Yes.
Yeah, x equals x for sure. So x equals x. You with me here?
Yeah.
Then if x is equal to x, now we're just going to do some basic algebra. Subtract 2b from both sides, that gives you this. Divide both sides by 2, that gives you this. Contradiction. Why is that a contradiction?
Because an integer can't be a fraction.
Yeah, we know that an integer minus an integer is,
An integer.
is 1/2 an integer?
No.
No, so that's impossible. So this is our impossible thing that we know is always false. Subtracting 2 integers and getting 1/2, that's always false. So we've shown our contradiction. We usually do these back and forth arrows. That's 2 arrows pointing at each other. Sometimes it's hard to know what it is unless you watch someone write it. That's 2 arrows pointing back at each other, back and forth at each other. That's usually what we do when we demonstrate our contradiction to call attention to the reader. Hey, here's our contradiction. You just read it. Okay, so we just really showed this implies a contradiction, something false. Therefore, x is not both even and odd, and we're done. Right? Because if it were both even and odd, then a minus b, then 1/2 would be an integer, right? Which is impossible. That's an impossible worldview. That can't be true. Good? Let's do another example. If a and b are real numbers, then the equation ax plus b equals to 0 has at most one solution. So, our antecedent, a and b are real numbers. Our conclusion, ax plus b equals 0 has at most one solution. We're going to do a proof by contradiction. We're going to assume a and not b and show that implies something false. So, I probably should have said assume to help you see it better. Assume a and b are real numbers and that ax plus b equal to 0 has 2 solutions. We're going to call them x1 and x2. Since they're 2 solutions, they're not equal. That's what we mean by 2 solutions. We mean they're not the same number. So assume by way of contradiction that we have 2 solutions to this equation. Wait a second. Is having 2 solutions the opposite of at most one solution?
No.
What's the opposite of at most one solution? More than one solution. So if you have more than one solution, you for sure have two solutions.
Yeah.
So if we show you can't have two solutions, then you definitely couldn't have more than one solution, right? So a little bit of thinking there to make sure that, okay, yeah, we didn't actually cheat. All right. So once again, so we assumed A and not B, and we're going to show that leads to contradiction. Okay. Well, I know that AX plus B is equal to 0, right?
Yeah.
Or AX1 plus B is equal to 0. And I know that AX2 plus B is equal to 0. If they're both equal to 0, then they're both equal to each other. Everyone good with why these two are equal to each other? Okay. Subtract B from both sides. Divide both sides by A. And we got x1 equals x2. We assumed that x1 and x2 were two different solutions, and we concluded that they're the same solution. That's impossible. You can't have x1 and x2 be different and the same. That's our false. You with me? So there's our contradiction. Therefore, ax plus b equal to 0 has at most one solution. And we're done. Any questions on that one, or should we just do one more?
We can do one more.
Move on. All right, next one. Proof. Two consecutive integers cannot be even. You can't have two consecutive integers that are both even. Makes perfect sense, right? So let's prove it. Assume by way of contradiction that there are two consecutive integers, x and x plus 1, that are both even. And we're going to show that this leads to something impossible. Since x is even, then we can write it as x equals 2a, where a is some integer, right?
Mm-hmm.
Then x plus 1, substituted for x, we get is equal to 2a plus 1. But if x plus 1 is equal to 2a plus 1, then x plus 1 is odd. Right? You remember the definition of odd?
Yeah.
Okay. So we have x plus 1 is even and x plus 1 is odd. Where did we say x plus 1 was even?
At the first.
Right at the beginning. Assume by way of contradiction that there exist consecutive integers x and x plus 1 such that they're both even. We showed that if x is even, x plus 1 is odd. So that means x plus 1 is even and odd. How do I know that's a contradiction?
So you're saying you can't.
Because of what I just proved over here. Don't rely on your intuition, rely on what you proved. So that's our contradiction, therefore no two consecutive integers are even. Make sense? Do we have any questions about this? All right. So I'll stop the recording. You can ask me any homework questions and we'll start the tests.